Welcome to the Science Edit, the podcast that breaks down the trickiest parts of science and helps you get it right when it matters most. I'm Miss Lima, and I'm here to support you with the science you need when you need it. Whether you're revising for exams, exploring future careers, or just trying to figure out why your last test didn't go so well, you're in the right place. Let's dive into our next episode. Welcome to this episode of the Science Edit. Today's a little different. We asked students to send in any science questions they were curious about, and we've picked some of the best to answer. I'm joined by 3 teachers, Mr. Hoskins, Mrs. Hillier and Mr. Devenold, and between us we have 66 years of teaching experience. From black holes to allergies, colour blindness to dinosaurs, we're diving into the strange, the serious and the downright fascinating. So, if you've ever wondered what Schrödinger's cat really is, or whether time travel is possible, stay tuned. You might just find your answer. Thank you everyone for joining me today.
Hello.
You might not find your answer. We'll find out shortly.
Well, the first question I hope everyone's going to be able to answer, because the first question is, why did you choose to become a teacher in the first place?
Mr. Devenold, why don't you take it away?
I got involved in leisure centres. I did a leisure degree, a leisure management degree, and for whatever reason chose to get into managing leisure centres. I did that for 10 years. I always enjoyed the coaching side of things, less so the management, and with the change in circumstances I had the opportunity to sort of start again, and I came to Oakwood in 2007 as a trainee teacher. I was lucky enough to be employed the year after by Mr. Moody. And I've been here ever since. You cannot get rid of me, 18 years on.
I was about to say the same, we can't get rid of you.
Yeah.
I think the thing is, though, is, you talk about, say, 66 years of teaching between us. No day is ever the same. It's different every single time. The challenges that the job gives us.
So you also say that experience, you make out that experience is a positive thing, that's sort of somehow guarantees you to be a good teacher. But I don't think, you ever feel that you're a good teacher, do you?
No, the job's never done.
No.
You can always get better.
No.
Yeah.
So why did I become a science teacher? Well, it really came down to the fact that I wanted to get into education. At university, I was heavily involved in a martial arts club, and I started teaching the younger years in university when I was in my 3rd year. And I discovered that I really enjoyed teaching. And when I came out of university, I was looking at really what I could do with my degree, and I saw that there was a big shortage in physics teaching, and I love physics, so why not? Got involved.
So how I got into teaching, through very similar to lots of other teachers, it kind of just fell into my lap, and the reason I've stuck at it is because I loved chemistry, and I'm just absolutely honoured and so lucky to be able to pass on that knowledge to other people who get to love my subject as much as I do.
It is the best subject. Let's face it, it's, without doubt. There's so many different branches, so many different careers you can move into as well. Let's go on to our first question, which I'm quite excited about actually, because I know it's something to do with a box, and then I kind of get a little bit lost. So what actually is Schrödinger's cat, and how does it work? That was sent in by a Year 8 student.
So Schrödinger's cat is a bit of a thought experiment about whether you know what you know, or what you think you might know. So a cat in a box, is it alive? Is it dead? And you will only find out once you open the box and make that measurement. The thing with Schrödinger's thought experiment was, when you open that box, you release a poison and kill the cat. So is the cat dead? Is the cat alive? Well, once you make that measurement, you will find out. And it's not really an experiment he did. Some people seem to think that it is something that was real.
I mean, I have my own Schrödinger's, not cat, but I have a Schrödinger's mouse situation going on in my house at the moment, where my cat has brought in a live mouse and she let it go. It's in the wall. And until I get home, it's both alive and dead until the moment I open my front door. So
You don't know. You don't know. You don't know until you make that measurement.
Yeah, I love it that you're just bringing science home with you. I do. That dedicated
science
to the job.
is everywhere.
Okay, so I've got another physics-based question. What is the physics behind black holes?
What most people know about black holes is that they are a very extreme... Well, in fact, let me throw it... Mr. Devenold, what do you know about black holes?
What do I know? Well, all I know is that it's possibly to do with a star imploding, and that it pulls matter in on itself. You get what's called the event horizon, and anything within that event horizon is black. No light escapes, is that right?
That's a really good place for us to just start and build upon. So when a very large star supernovas, its core will collapse and form a gravitational field so strong that inside what you mentioned, the event horizon, the gravity is so strong that not even light itself can escape that. So it's an extremely strong gravitational source, and no object can escape that event horizon once it enters it.
Is that no object? Because I believe Hawking radiation can escape, and that is the black hole eventually will end through the radiation, Hawking radiation.
Yes, so Hawking radiation is something, so that the black hole sort of excretes what is known as Hawking radiation, and eventually, we're talking hundreds of billions of years, the black hole would no longer be a black hole. However, that's all very much based on the theory being exactly correct, and in science, no theory is exactly correct. They're just very good approximations of reality. I think the other thing to say about, I think that people might be interested to hear about black holes is, so what happens is the gravitational field is so strong it bends space-time itself. Yes. And so we've actually got images of space where we can see what's known as gravitational lensing, where the big gravitational field bends light similar to the way that a lens bends light in your glasses. And so we've actually got photos of a black hole taken a few years ago for the very first time, where you could see the light warping round a black hole.
Was that James Webb?
It wasn't the James Webb Space Telescope. That was actually a combination of radio telescopes on the surface of the Earth and a very clever bit of mathematical algorithms to sort of piece them together to make like a almost world-size radio telescope in order to image something so very far away in the centre of, I think it was Sagittarius A. I can't quite recall exactly.
Something that my students always seem really interested in is the idea of spaghettification. Have I said that correctly?
Yes, spaghettification. So as you approach a black hole, the gravitational field is stronger the closer you are to it. So when you cross that event horizon, let's say you go feet first, your feet will get to a point where the gravitational field is so much stronger on your feet than it is on your head, because gravity has the inverse square law. So when you double your distance, you have 1/4 of the strength. So there will be a distance from that singularity, the very center of a black hole, where your sort of atoms from your feet will be stripped off at a much quicker rate than from your head. So you will be spaghettified.
I have a question. What happens to the matter that enters a black hole?
So that matter ceases to exist as itself. So the gravitational forces literally strip the atoms apart, so they're no longer atoms. Electrons get forced into protons, becoming neutrons, but then protons and neutrons, etc., are made of quarks, and everything gets forced down into a singularity, which we don't really know how that works. It
takes us back to the comment you made earlier that physics is, and most of science is theory based, isn't it? And from that sense, it's born, it lives, it evolves, and either more evidence is sort of comes along to either prove or disprove it. And if it disproved, then it dies, and something else, another theory takes its place.
That's exactly the beauty of science.
So the next question is, how can we tell what the universe looked like 14 billion years ago? Goodness me.
Anybody else want to lead on this one, or should I start again?
This was another Year 8 student.
It's a lovely question.
Well, I'll have a go, because my basic understanding of science, and certainly during my lifetime, you guys are a little bit younger than me, but I remember when the Hubble Space Telescope was launched, I think around 1990, and seeing the first unbelievable images coming back into deep space. And I think
the Hubble Deep Field.
Yeah, and I think that certainly sparked an interest in me. All of a sudden, the universe became a little bit more understandable in a way, and a little bit more real. And it certainly sparked off in my head: was there life? What was out there? And obviously that's followed on by the James Webb Telescope that you've.
Okay, so Mr. Devenold has just mentioned the Hubble Space Telescope, and I mentioned the Hubble Deep Field. So what I want you guys to imagine, those of you listening, get a postage stamp, cut it into a quarter, hold it at arm's length next to the moon, and it will be less than the size, it won't even cover up the moon. The Hubble spent a whole week focusing at a patch of sky that large, and it exposed a very long exposure film, and when that image was then processed by computers, they discovered hundreds of galaxies, and this surprised scientists to really see. So what we started seeing was galaxies so far away that we got a greater understanding about the universe. And so to go back to that question about how do we tell what the universe looked like 14 billion years ago, we have to look far away because light takes time to travel. And if we want to see light from 14 billion years ago, we have to be able to see 14 billion light years away from us, because that's how long light has had to travel. A little bit of a simplification there. And this is where the James Webb Space Telescope, the latest one which launched a few years ago now, it images in the infrared, because light, which has travelled 13.7 billion years, has been travelling through an expanding space for all that time. So it is redshifted way beyond the visible light spectrum and exists solely in the infrared spectrum.
Am I right in saying that the universe is projected to be 15 billion years ago? Is that right or not?
I thought it was 14.7.
13.7.
Yeah,
So
13.7 billion
The point
years.
I was making was it has. So it has gone back to the Big Bang. We can.
Well, I think we've recently seen from a James Webb Space Telescope. Again, I'm not an expert on the James Webb Space Telescope, but from what I've done on my interest, like reading outside of work, is that we have imaged some of the oldest galaxies that formed just a few 100 million years after the Big Bang. Right. And so we're still fairly confident that the universe is 13.7 billion years old.
Have you heard of the theory that obviously the space is expanding, but it's going to get to a point of expansion and then it's going to start retracting on itself?
Yes, indeed. This is something we look at in A-level physics. We look at the fate of the universe. And so we look at the critical density of the universe and how that would affect. So, yes, you're right. If gravity is pulling everything in, that the expansion of the universe should be getting less and less and less, and depending on the density, it might forever get slower and slower and expand forever. It might, however, get to a point where it stops expanding and then contracts back down, and that theory is called the Big Crunch, a very nasty end to the universe. However, in the 1990s, we discovered that the expansion of the universe was actually getting faster. And that is a very curious thing indeed. And what we don't really know why the expansion's getting faster, it's been dubbed dark energy. And to really throw a spanner in the works, we think physics is all, and chemistry and biology are all about done when we finished the periodic table and started discovering the electron, proton and neutron. Well, physics says that dark energy accounts for about 70% of all energy in the universe, and actually the ordinary energy and matter that we see around us is only about 5%. And the mathematicians among you may have been like, hang on, what's the other 25%? Well, that's dark matter. Again, something we don't really know what it is. So actually, we only know about 5% of what's out there.
We are scratching the surface.
We are only scratching the surface,
so
exactly.
If we talk about the Big Crunch, would that affect time?
Oh, that's a lovely question. So, what is time? When did time start? We don't really know. We say that the Big Bang was the birth of time, but we don't really know if before the Big Bang there was time. We just have no actual way of telling that. So there's some interesting questions there. Another thing with black holes is stronger your gravitational field, time will be different for different observers. It's all relative.
Well, that's actually another question that we've
got.
It's
a human construct, isn't it?
It is.
Time.
One question we've had is, can you time travel?
Oh, that's a question I get asked quite often. I would say yes, but not into the past.
Well, in terms of time travel, isn't there something along the lines of that, Mr. Hoskins, in regards to theory of relativity?
Yeah, so in Einstein's theory, it states, or one of the realizations is that the faster you go, the closer you travel to the speed of light, the slower time passes for you. And this is like a really confusing idea. The way I try and understand it is if I'm traveling faster, the signals that my neurons have to travel becomes increased distance. So although the signal may travel at the speed of light, because I'm traveling closer to the speed of light, the path that they're traveling along my neurons increases. So therefore I don't age as much. It's not quite a great explanation, but it's a way that you can help understand that time for you would be slower. And this isn't some sort of myth or sort of idea. We know it from astronauts. We can give them the most accurate watches in the world, synced perfectly, and an astronaut who's in the International Space Station for 6 months will come down 6 months later and they will be a second or two younger. They're only travelling at an absolute fraction of the speed of light. But if you travelled about 99.99999% of the speed of light for a year, and you went off into space for that year and came back, the Earth would have gone around the sun multiple times, and you will be in the future.
I mean, it's fascinating, but I think the one thing about time travel, when people ask about it, is the concept of being able to go back in time, which obviously is not.
I'll tell you what always
plausible.
amazed me was the idea or concept that you could take off from a plane in London and see the sunrise, travel across the Atlantic to New York and see the sunrise again in the same day.
Yeah.
And that was Concorde, of course. And Concorde travelled faster than the rotation of the Earth. And so therefore gave you the idea, if you like, or the feeling that you had time travelled in some sense.
The only way you could travel into the past, according to the laws of physics, which, again, you need to break the laws of physics because you need to travel faster than the speed of light. So if you can imagine yourself like a hourglass shape, like sort of like two lines intersecting, and you're at the point where they intersect, and the line to the right and to the left in forward in front of you, that's if you travel off to the distance at the speed of light. And the lines going back behind you are where you could have been if you travelled at the speed of light to where you are. The faster you go, the more those lines start to sort of become horizontal. And eventually, if you could go fast enough, those lines could be horizontal, meaning you could have been anywhere in the past and you could be anywhere in the future. And then you need some sort of way of sort of going from one to the other without through your location. And that's where the idea of like a wormhole comes into things. It's not something which has ever been observed or any proof
Except in the movies.
Except in the movies, yeah. But that's the only way you could travel into the past. You'd need to travel into this past the speed of light, and then you'd need some way of generating a wormhole.
So what you're telling me is I'm never going to be able to go back to 1955 and dance with Marty McFly.
Back to the Future.
No, I mean, I was just talking this with some pupils the other day, the idea of the Bill and Ted time travel, where you could go, if I ever go into the past, I will put a winning lottery ticket in my wallet on this morning, but I know I haven't checked my wallet today, so if I open my wallet right now, there's no winning lottery ticket there, so therefore I didn't come back in the future. I didn't come back to this day and plant a winning lottery ticket in my wallet.
That's a really interesting point if you think about it. If time travel in the future, to the extent that our listeners are thinking of when they think of time travel, if it ever does become possible, it would have been evident by now. We would have seen someone from the future by now.
Travel to the past breaks the law of cause and effect, creates paradoxes. So just on that little bit of theory, I know it's a bit of a boring answer, but you can't travel to the past.
Unless it creates parallel universes.
Oh, getting into
That's
the Marvel
another
world
question,
now.
isn't it?
Yeah.
We've got one more.
Go for it. Go on.
sorry.
I was just going to say, so we, coming from America to France, coming back 6 hours in time, or summer and winter time going forward and back, we don't consider that to be time travel.
I mean, I wouldn't. I think just because we are still aging in that process, and just because we've physically moved from one position to another where there are different time zones that us as humans have put in as a construct, I wouldn't necessarily.
I mean, I would say I'm here right now next to you three, and if I go to a different time zone, you three aren't still here at this exact same time. So it might be 3 o'clock to me in the afternoon in America, but where are you? You're not still here at 3 o'clock in the afternoon.
Okay, we have one more question I think we're going to have time to fit in, and that is, why do some people sneeze when they look at the sun?
Of us around the table, who does this affect? Who can look at the sun and sneeze? Or
Not me.
If they have well, I suppose there's two parts to this. So if I look at the sun, I won't sneeze. But if I need to sneeze, if I look at the sun, I can do. So if you know when it's building up and it's just there, it helps.
I have an issue with multiple sneezing.
Oh.
So I will very rarely sneeze, but when I do, I can sneeze 20 or 30 times.
Wow.
Yeah.
What is the...
Unbelievable.
I want to know what the world record is for the number of sneezes in one go.
I
I'm
can
up
actually answer these questions.
Really? Can you?
Miss Lima,
it's
take the
biology,
mic.
isn't it? So, I mean, what you're describing there as multiple sneezes is a threshold. So basically, the sneeze reflex needs a certain threshold of stimulation, and what you're finding is that one of your sneezes is setting the threshold for the next one, so you'll carry on doing it. Mrs. Ilya's question about how many people here actually affects, it's actually then two of us, because I have this too. If I need to sneeze, I can look at the sun and I will do so, or any light to come to that. And actually sometimes light will just make me sneeze, even if I don't
know
feel
what I'm
like I
going to
need
do
to.
next time I need to sneeze.
It works.
Well, no,
A little
it won't
scientific
work.
experiment.
It won't work. Yeah, it won't work because there's a very clear reason why it will work for certain people and not others. So it's all to do with how your visual cortex develops in your brain. Your brain's developing. So the neurons that control the sneeze reflex and the neurons in your visual cortex actually run very, very close to each other. And if you think about how the brain develops, your brain will be slightly different to mine, and it's just that slight interference where you're getting visual neurons stimulated, and the interference from that is then stimulating the sneeze reflex.
This is similar to why some people get a gag reflex when they stick some things in their ears.
It's exactly the same. Yeah.
I believe this affects 10 to 35% of people.
I always ask.
I can't believe that.
No, it depends. It is around about 20% of people, but it can vary. I do ask my classes when I teach it.
50% in this room.
It is,
Well,
so it just varies. It depends whether you've got a representative sample or not, which is another scientific.
Good term. Good term.
Another podcast for that.
Yeah.
Well, saying that, I mean, that's all the time we've got for questions today, but we definitely do have more questions, and we will be running another episode. Thank you so much for listening to this episode of Ask Me Anything. We loved hearing your questions, and if you've got more or just want us to tackle something specific in a future episode, please just drop us a message at contact@thescienceedit.com. Don't forget to follow the podcast on Spotify, and we'll see you next time. Thank you so much, everybody.
Thank you.
Thank you.